Now we're going to do problem 14-17. Problem 14-17. And it says if the cord is subjected to a constant force of 30 pounds and the smooth 10-pound collar starts from rest at A, determine its speed when it passes point B. Neglect the size of the pulley C. Again, notice there's no friction because it says it's smooth. It's a smooth collar. And remember, when we have these cable problems, it's always important to remember that if we don't have friction involved, all we have to do is focus on how far the cable has been pulled. That's all we need to do. Now, if there's friction, it gets very complicated. But here, if there's no friction, we're just focusing on how far the cable is pulled. And so again, we have a picture, something like this. We've got some kind of a curved rod going up here. And so starting at A up here, then there's a collar along here. And it's going to start at A, and A is 1 foot back. And then it's going to be pulled up to B, and B is 3 foot from the end here. And then there's a pulley over here at C. £30 force being pulled down. And 2 feet like this. And this is 4.5 feet. From the bottom here. And so the question, again, when you're dealing with something, when you have a cable like this, actually this is not, at the beginning it'll be, it's kind of pulled up, it's being pulled up this way, then it's going to end up here at B, but it's going to start at A. So the question you always want to ask yourself is how far is the pulley being, or is the cable being moved? How does that maybe translate? So the cable is being pulled this way. And so the best thing, so we're going to start at A and go to B. What we can do is figure out like the distance from A to C when we start and the distance from A to B at the end. So, so at the start, find the distance from A to C. So we can make a little, maybe a little picture. So you can see where A is over here. So this is going to go maybe something like this. This is A, this is C. And you can see that from A to C, the horizontal direction is going to be 1 plus 3 plus 2, so that's going to be 6 feet. And then the vertical distance is 4.5. So this distance from A to C, like the length of cable that's going from A to C over here, is going to be the square root of 6 squared plus 4.5 squared. And we put that in your calculator, that's going to be 7.5. That's going to be the distance the cable is from A to C. So that's going to be like, say, the start. At the end, we want to know, so it's going to end over here. So we want to know the distance from B to C. And so there it's just simply going to be like this. The cable is just going to be up here. So it's going to start like over with this length. It's going to end up like this. And again, you can see from our picture, that's going to be just 2 feet. So the cable moves 7.5 minus 2, or 5.5 feet. So then the work from the force of the cable, from the force on the cable, again, remember, it's just simply going to be the force times the change in the distance. So it's just going to be, and the force is 30 pounds, 5.5 feet. And that's going to be 165 foot-pounds. So that's going to be the work done by the force. And then the work of the weight, remember, it's always just going to be the vertical distance. So that's going to be the weight is going to be the weight times delta y. And again, our weight of our collar, we're told, remember, that was 10 pounds. So that's going to be 10. And then remember, delta y is just the vertical distance. So the collar started down here at A, and it ended up at C. It's gonna be at B. And so it went from, let me just show the picture here. It started at A, ended up at B. So it changed 4.5 feet. Remember, all you care about is the vertical distance. Doesn't matter if it took that odd path to get there. And that's what's nice about this, is that you don't care about what path it took. You're just interested in the vertical change. So we get that. And so now, so that's the work done. And then we need our initial kinetic energy, 1/2 mv1 squared. Now it starts out from rest, so that's just gonna be 0. Our ending kinetic energy, 1/2 mv2 squared, is gonna be 1/2. Remember, our mass is 10 divided by 32.2 times our velocity, and that's the velocity at B that we're gonna end up, that's squared. Up a little bit. So now we have everything that we need, don't we? We can just put in, so again, put this in 0 plus 165 minus 45 is equal to 1/2 10 divided by 32.2 VB squared. Just put that on your calculator and you get VB equals this 27.8 feet per second. See if there's any questions on that. Any questions at all? Okay. If not, we'll go to the next problem. And that's going to be on your handout or from your book. It's 14-22. And often you have to do these problems in steps because like the forces change. Now we're going to take a look at this problem. 14-22. The 25-pound block has initial speed of 10 feet per second when it is midway between springs A and B. After striking spring B, it rebounds and slides across the horizontal plane towards A, etc. If the coefficient of kinetic friction between the plane and the block is 0.4, determine the total distance traveled by the block before it comes to rest. It asks for the total distance. We'll kind of find out the sort of final position where it ends up. And then if you want to, you can add up all the values, but we'll find out like where the final position is that the block ends up at. So in 14-22, we have this block. And we have the point B here. And we're told that this is 1 foot. One foot over here. And we have a spring here. This is A. And we're told the spring constant is 60 pounds per inch over here. And the initial velocity is this block. It's starting from this point right here, which is 1 foot away. The initial velocity is 10 feet per second. And so we're going to have to, and there's going to be friction in this case. And so we're going to need to first find what the friction force is. Remember, to do that, we can sum the forces in the y direction like this, even though there's not going to be any acceleration. Again, this is a 25-pound block. So if we sum the forces and find like the reaction, so NC minus our 25 pounds is going to be equal to, there's no acceleration. So we can see the normal force is going to be 25 pounds. And then therefore the friction force, remember that's just going to be mu times your normal. And that's just going to be, we're told that the friction is 0.4 times 25. And I guess that's just going to be 10 pounds, huh? 10 pounds force. So we have our friction force. So now again, this block is moving it to the right, and it's going to hit the spring and it's going to compress the spring. So we almost have to do this in several parts because, again, from here to where it hits the spring, there's just going to be like friction on it. But then once it compresses the spring, there's going to be spring force. So we're going to have to look at this. So from the start to point B, so let's see what we want to do. So from the start to point B, so our T1 is going to be 1/2 MV1 squared. And again, that's going to be 1/2 25 divided by 32.2. And we're told it's starting at 10 feet per second. So we'll start with that. And then we're going to want to find out what's going to happen when it gets to B. 1/2 MVB squared. So we 1/2 the same thing, 25 divided by 32.2 VB squared. And then the only work that's going to be done is going to be due to friction. Remember, since there's no other forces acting on it, so F. And then that's going to be times the distance that's traveling. And again, that's going to be 1 foot. Notice from where it starts to point B, that's just going to be 1 foot. So that's going to be 10 pounds force times 1 foot. So then if you put this all into T1 plus summation U from 1 to 2 equals T2. And T2 is going to be at B. Let me just put that down just to emphasize it. So again, if you put all these in, put this in here, put this in here, put this here, you'll find the velocity when it gets to point B is 8.62 feet per second. Any questions so far? Again, so that gets us to point B. So now it's going to compress the spring. So again, force is going to change. So we're going to have to go. So from this point, we'll, so it's at point B. So it's going to start to compress the spring. So we'll now look at from point B to the point when it stops. So it's still moving. It's going to compress the spring. And so from that to where it stops. So from B to the stopping point. And so once again, let me do this sort of in a shorter way. I'll actually just put everything into T1 plus summation U1 to 2. And again, T1 is going to be like, say, point B, and T2, say, where it's going to stop. And so when it's starting at point B, we just found that the velocity was 8.62 feet per second. And so let's, so it's going to be 1/2, 25, by 32.2, 8.62 feet per second squared. and there's still going to be friction. Again, remember, I don't know if I made it clear in last week, friction's always going to be negative. So there's going to be that negative friction force. Which is going to be 10 times the distance. Now, we don't know what the distance S is yet. So I'll just put that down as S. Then minus 1/2 times, let's see, 60 times S squared. Remember, this is for like a spring. Remember, for spring, it's going to be 1/2 KS squared. And again, on the right-hand side, it's going to be this, but that's going to be where it stops. So that's just going to be 0. And so, so let's see. Yes, we have this. And so if we multiply things out, we get minus 30S squared minus 10S plus 28.84 is 0. And so we just have to use a quadratic formula to solve this. So it's to be 10 plus or minus the square root of minus 10 squared minus 4 times minus 30, 28.84 divided by 2 times divided by minus 30. And so when you put that in your calculator, you get 0.8279 feet. Yes, I know. You're gonna ask about the spring constant. Yeah, I did it. Okay, I should have mentioned. I did it the way they have it marked here, and then I didn't get the answer that they had in the back. Then when I think I think I did write this wrong at the beginning. So even though they wrote 60 pound per inch, I think they meant 60 pound per feet. Is that what you're gonna ask? Yeah, I think that must be a typo because yeah, I'm glad you brought that up. Because when I did it with the 60 pound per inch, I ended up not getting what they got. Yeah, thanks for bringing up. Yeah, so on your handout there, make that 60 pound per foot. Uh-huh. Oh, yeah, sure. This one here, a particular part. Good. Everyone got everything? Yeah, so I change that, yeah, to 60 pound per foot. And then so we get this. So now that's going to be, so this is from B to where it's compressed. So that's saying like this is compressed 0.8279 is what that's going to be compressed right there. And then so now it's been stopped. So now we have to go from the stopping point back to point B. So again, so we have to do this in a lot of steps. So from stopping point back to B. So So once again, let's do the T1 plus summation of the work equal T2. Again, T1 is going to be, say, the stopping point, and then T2 is going to be back to B. So let's maybe write it that way. So again, at the stopping point, it stops. So the T at the stopping point is going to be 0. And then it'll be 1/2 60 0.8279 squared. Again, that's for the 1/2 K S squared. And then minus the friction force. Again, that's going to be your friction force times your delta S, which we said was 0.8279. And then the point B, it's 1/2 25 divided by 32.2 VB squared. So put that big mess in your calculator and you get VB is 5.625 feet per second. Now, of course, the reason it's different is because of the friction, because the friction slowed it down. Otherwise, it would have been like, say, if there was no friction, what would happen? It would be the same velocity at point B when it ended as it was when it went into originally hit point B. So now finally, so we're back at point B. So now from point B to the final position. So again, T at B, summation 1 to 2. So let's say final. And so that's going to be 1/2. Again, the point B, it's 25 divided by 32.2, and then the velocity is 5.625 squared. And again, when it's moving, say, from point B, when it's out in that open area, all there's going to be is just going to be friction minus 10 times, I don't know what you'll call this, maybe D, distance D. And for the final, it's going to be 25 over 32.2. Is maybe where it finally comes to rest. So it's just going to be times 0. And when you put all that in your calculator, you get something like 1.228 foot. So what that's going to mean is that, just to get our position right here. So if this is point B, then it's going to end up its final position is 1,228 feet from there to end up something like that. Any questions on that? It's kind of a long problem. Next, we're going to look at the section 14.5, conservative forces and potential energy. And this is a short section. It's mostly going to be used in the next section after that, section 14.6. And so we need to first explain a conservative force. And this is a force which produces work that does not depend on the path. So it depends only on the initial and final position. And some examples, the work done by a spring, and the work done by a weight. These are would be considered conservative forces. And not friction. Friction is not conservative. And so that'd be an example one that wouldn't be. And then, so that's just a definition of conservative work. Another thing we need to talk about is energy. And energy is the capacity for doing work. And we have two types of energy, kinetic energy that we already talked about. And again, this is associated with motion, which we just saw. Remember, that was like our 1/2 mv squared. This is always associated with motion. And then we have potential energy. And it's associated with, could be like position. Or we could also have like, say, associated, like, or it could also be associated with elasticity, you might say. And this would be like, so we'll say springs. And we'll see this in more detail here in a minute. So let's look at a little bit more specifically here. So, again, so for potential energy, like we're going to have like it due to weight. Now it's going to be a little bit different than before. So potential energy so what is going to be like Vg equals Wy. Now this time it's similar we had in the last section, except This time, y is the distance above or below a datum line. And so if the particle, let's say if the object or particle is below the datum line, then it's negative. And Vg is positive. Object is above datum line. So remember in the last section, if you were moving something from a higher position to a lower position, then the work was, or if it went from the higher to the lower, the work was positive, and it went from the lower to the higher, it was negative. And now what we have here is that we're talking more about where it's setting. Like, so again, if you have like a picture, you do a picture like this. So you have a datum line here, and you have like some object up here, then Vg is positive. If the object is down here below the datum line, then Vg is negative. And again, kind of the idea is that if it's sitting high above a datum line, it can do work by kind of falling downward. You know, let's say if you, say if it's on the end of a cable or something, if you let it drop, it could do work. So therefore, it potentially has like some energy. On the other hand, if it's below the datum line, to move it upward, it would take work or take energy. That's sort of just a vague idea. So in this section, what we're going to have, we're going to do conservation of energy. And it's going to be T1 plus V1 is T2 plus V2. Again, this is going to be like kinetic energy. And this is going to be potential energy. Kinetic energy, potential energy. So in other words, the total energy to start is going to be equal to the total energy at the end. And this works if you only have conservative forces. Like say no friction, no forces that depend on path. And see what else. And so it would include stuff like springs and weights. Those would be the things we're going to do next.